So just to kind of give you an example of how this all works, thanks for bearing with me through this whole sort of development. This is Lorenz 96 system, so you've probably sort of seen this before. We're using what's considered a hard test case configuration. So we're observing, so f equals 8, sort of in this chaotic regime. We're observing every other component of the state, and the time between observations is large, 0.4, which is going to allow the state to kind of evolve more non-Gaussian features. Now, what I want to do is sort of compare this filter that we've constructed, calling the localized nonlinear filter, with a state-of-the-art ANKF from Ley and Bickel. And if you look at, say, for a certain number of particles, for 400 particles, so how are we evaluating error? Unfortunately, I'm not evaluating error by telling you how close we are to the true Bayesian solution, because I do not know the true Bayesian solution for this problem. And with a particle filter, at least a simple particle filter, there's no way you can compute the true Bayesian solution. Maybe with enough computational resources and something like a space-time particle filter, a la Dan Krizan or something like that, you could get closer to it, and that would be an interesting sort of offline calculation to do. But for now, we're just comparing tracking error, root mean square error, and how well we track the state. And of course, this varies over time and iteration. So we're looking at the median, the average, and the variance of it. And the localized nonlinear filter does quite a bit better than sort of this previous ENKF. And if we reduce the number of particles, another interesting comparison is to say, well, what's the impact of nonlinearity? Because there's really two things at play here. One is the sparse Markov structure assumption, and one is the nonlinearity of the maps. So one thing we could easily do is just turn off the nonlinearity, keep the sparse Markov structure assumption, and see how much we gain. So for this number of particles, by basically going from linear filter to nonlinear filter, we're still actually able to gain a lot. This is about a 25% gain in RMSE. I think in this business, for this particular problem, is pretty good. So how exactly did we do it? Well, so the Lorenz 96 has this 40-dimensional state. The Markov structure we chose involved 5-way interaction, so each node interacted with 2 neighbors on the left and 2 neighbors on the right. Observations were assimilated one at a time, so these red are the observations attached to every other state. And then what map did we learn? And here there's a lot of freedom. So we used a nonlinear map. The particular nonlinear map we learned was separable. And in particular, these are sort of just basically a linear map plus some radial basis functions that capture some nonlinearity. Of course, much more general parameterizations are possible. The fact that this map is separable actually makes that convex problem even easier. It just turns it into a regression problem. But in general, this is just one possible choice. And I think there's a universe of possible choices out there to be explored. And okay, how well does it do kind of just visually? So this is the state of Lorenz 96. This is time, and you can see you have these kind of left-running waves. This is the truth, and this is the mean of the filter, and it's able to track it pretty well. So the upshot is that introducing these kind of simple localized nonlinearities has a lot of impact. But to be able to introduce nonlinearity, you really have to introduce sparsity at the same time, because for a limited number of samples, for a limited number of ensemble members, there's no way that I can learn an arbitrarily nonlinear function. We need to regularize the problem in some way. And so sparsity provides a way to do that. So what's kind of the upshot of this? Well, we constructed nonlinear transformations that simulate conditioning on data. So in philosophy, this is like an ENKF. There's no weights. There's no importance sampling. There's nothing that's going to degenerate. We are necessarily accepting bias. Why? Because if I wanted to do this exactly, the maps S would have to be essentially the inverse of the Noeth-Rosenblatt rearrangement for the true forecast. And the map T I have to learn will be actually the sort of Noeth-Rosenblatt rearrangement for this mapping from the reference to the posterior. But I'm not looking at all possible maps. I'm certainly not capturing the true Noeth-Rosenblatt rearrangement. There is bias due to my chosen parameterization. And there's also bias due to the fact that the Markov structure that I assume to be true as a regularization device may or may not be true. But I would also claim that in this game there is no way that we ought to trade some variance for bias. We ought to allow some bias, and that we can get much smaller error on the whole if we trade some variance for bias. And for limited numbers, limited ensemble sizes, there is no way that you can characterize in an accurate way, a 40-dimensional, much less a million-dimensional distribution. So we have to sort of introduce these devices to regularize the problem, and that gives you some price of bias. But what the upshot is that you should be able to trade that bias. You should be able to allow richer transformations that can capture some of that non-Gaussianity of the prior and the posterior. So the choice of map, the nonlinear functions that you use, and the sparse Markov structure regularize the problem. In particular, the idea of regularizing by sparsifying the Markov structure allows a lot of the operations to be made local. And this is really essential to kind of scaling the whole algorithm. Okay? So, of course, a lot of extensions to this. You could think about harnessing decay of correlations in that propagation step. So I simulate here. We push the information further out on the state. At some point, you could just stop pushing because observations here won't affect things farther away. You could actually do conditional sampling in parallel based on graph decomposition. So there's a lot of sort of machinery one could bring to bear from graph theory. Here we just imposed a Markov structure and with a limited number of samples. I think that's really what one can do. But you could also imagine maybe learning the Markov structure, maybe learning it with some kind of L1 penalty. Think of it as a sparse recovery problem. So there's things to be done there. And there's a whole host of error analysis to be done as well. I just want to spend maybe my last 2 minutes mentioning something maybe we can discuss in discussion. I've sort of stopped talking about the smoothing problem and the parameter estimation problem. I want to come back to them very briefly. These are harder problems. I just want to mention some sort of parallel work where you could actually, in principle, if you had access to this transition density, if you could actually evaluate this and its gradients, then you can do something else that will actually give you smoothing and parameter estimation in a nice way. Essentially, the idea is to use this maps from densities approach to solve the whole problem sequentially. So the things that I'm talking about on this slide only are not really sample driven. They're saying I want to find a map T that pushes forward a standard Gaussian to this whole big smoothing distribution, and I want to update from TK to TK plus 1 in a recursive way. And the upshot of this is essentially you're going to solve a sequence of lag1 smoothing problems because this map T decomposes. So there's actually kind of a duality between the sparsity of the map S that I described and the decomposability of the direct map T. And that sort of notion of graph decomposition leads to some structure in T, and you can use that to solve the problem. And you can actually generalize this to joint state and parameter estimation. The caveat is this is all much more computationally expensive because this is basically trying to do much, much more. And it involves evaluating this transition density and its gradient. So in practice, that means you have the forward model, you have some adjoint. So this is really much more akin to things you would do in a variational approach. You need all the machinery, sort of a 40 var plus more. Some details in this paper on that, if you want to talk about that. So I'll just conclude, basically what I've tried to present today is ways that one could sort of take something that I think is computationally attractive, the NKF, in terms of performance, but generalizing it to non-Gaussian settings in a way that I think offers a lot of room for exploration in the sense of how you model the distributions of interest using non-Gaussian Markov random fields and using nonlinear transformations, using transport maps to represent non-Gaussianity. And I think, hopefully this is just a starting point for a lot of scalable algorithms because this just tries to do things on a local level as much as possible. So a couple references, and if you want to play around with transport maps, there's some code here that you can look at. Thank you very much.
Thank you very much. So if you have any questions, comments, also we have a discussion session later, but if you have questions now, I can take some. Any?
So it looks like the efficiency of the technique hinges on the sparsity. How do you compute it or do you impose it?
Right now we impose it. So just to go back to the Lorenz example. So for this problem, and sort of the states live in a circle, the graph, the sparsity of the graph that we impose is basically in this figure. So each node is connected to 2 neighbors on either side. So essentially 5-way interactions. And that's just totally something that we imposed. Now, is that a reasonable choice? Does the true distribution actually satisfy, does it have a neighborhood side of 5? Maybe, maybe not. But to really learn that, I probably need a lot of samples from the true distribution. So one could say this is something we could learn offline, given some samples from, characteristic samples from the forecast for the system. But right now it's just something we impose. But it's kind of akin to picking like a localization radius, just something you pick. So it's regularization through sort of brute force.
Because if you're solving like a true forecast system, like the weather or ocean, you have dynamic relationship between the different variables, and these are just geometry. They tell you essentially how things are correlated and related
So I mean, I wouldn't advocate picking the graph structure randomly. I think that embedded in, say, the fact that this works for the system, it means that this choice sort of respects something about the dynamics. And in particular, I mean, this is just saying that the forecast distribution, that each, this is for, of course, for all, this is a statement about conditional independence. This is not a statement about mutual independence. And conditional independence is a much weaker thing. So it's not saying that this node here is completely uncorrelated with the node here. They may be perfectly well correlated. It just says that conditioned on something in between, these guys are independent. So if there's sort of propagation of information, conditioning on something in the middle might still allow for long-range correlation. So in general, I actually think that, I mean, we played around with, this just comparing this to things like, covariance localization. And localizing the precision, which is the Gaussian analog of what we're doing here, is in general a much sort of more gentle hammer as far as regularization. But you would have to, of course, I mean, you're right. You have to account for physical interactions that matter. There's probably a lot of art there. Maybe you can learn the graph as well. That's the other alternative.
Here, I have another question, which is about the number of choices that you're allowed to do. So you have this structure that is given big, respecting some relationships where you have all this map.
Yeah.
So many choices, and you feel that you can run into
yeah.
Is it robust to all these personal choices?
Yeah.
No.
Well, I would say this is a great question. I mean, so in some sense, like we opened up the can of worms, right? Like, because if you had restricted yourself to linear maps, life is simple. And if you had, I don't know, well, I think people are already making a lot of choices as far as regularization already. But you're right. There's a zillion choices. What we find is that, a lot of these choices are motivated by some combination of what we think is physically reasonable and also what's computationally efficient. So computational efficiency dictates that we'd like to keep this neighborhood small, because it essentially gives you the sparsity of S, so that kind of restricts things a bit. And then also, we always can include a linear portion of the map, because we think we should at least sort of be as good as an ENKF, at least have that facility. And then this is kind of, you could imagine seasoning that you sprinkle in, nonlinearity sprinkle in. But what's the best? I mean, I would make zero claim that this is an optimal parameterization for this problem. To be honest, I have no idea. We're really at the start of figuring out what are good choices to do here. You're right. I mean, it's a bit disturbing that the universe is very broad. But I think this is the first step, and at least just seeing what that whole universe is, and then maybe we can figure out how to navigate through it. One thing that I would say, for the Markov structure, we have experimented a bit with learning Markov structure, and this, of course, is something people do in spatial statistics. Learning the Markov structure from samples, but then learning it in the non-Gaussian setting is interesting, because then there's a sort of back and forth between conditional independence properties and then the map that you use to learn things. So we have kind of a first attempt on it. We had a paper in NIPS last year about some of this stuff. But I think, again, there's a lot more to be done there as well. So yeah, the universe is broad, and maybe that's a bit disturbing, but I think it can work. It can give you something if you navigate well.